Hello all and welcome. We will be waiting for a few minutes, 2 minutes, for the rest people to join us, and then we will be able to start. Okay. Lynn, if you'd like to share your screen to have this as a background, and then in 1 minute I will start the introduction of you all. Perfect, thank you. Okay, we have several participants. And people is still connecting as far as I can see. Okay, I think that is a good starting point right now. Okay, so let's start. So good afternoon, everyone, and welcome to our webinar, which is entitled Driving Innovation in Sustainable and Self-Healing Polyurethane for Textiles, which is organized by SUBBIMATT Project. My name is Kate Trompeta, and I'm a chemical engineer from the National Technical University of Athens with a PhD in nanotechnology, so I will be the moderator for today's session. This will be the first webinar from a series of webinars that will be organized throughout the duration of SUBBIMATT Project, which will be held twice a year from now on. The webinar will be recorded, so I kindly ask you your consent for this, and then it will be uploaded to our YouTube channel for the project. So today we will start with the introduction to SUBBIMATT Project, and we will meet CENTEXBEL team, who is coordinating SUBBIMATT. The project scope will be presented by Dr. Lynn van der Schuren, and she holds a master and a PhD in materials engineering. Lynn has been working for 13 years as a project manager at CENTEXBEL and is responsible for European and private research projects in the field of extrusion of thermoplastic polymers, focusing on the use of sustainable bio-based materials for textile application. So Lynn will be introducing SUBBIMATT, which is an innovation action initiative funded under Horizon Cluster 4 Resilience Call in 2024 related to bioinspired and biomimetic materials for sustainable textiles. So let's begin. Lynn, could you start by giving us the overview of SUBBIMATT project? And we will have a question and answer session at the end of the project. So you are free to write down your questions in the chat or raise your hand, and all questions will be answered at the end after the second session. I would like to give the floor now to Lynn to introduce herself and start with the overview of SUBBIMATT. Thank you very much.
Thank you very much, Kate, for this kind introduction. My name is Lean, and I'm happy as a coordinator of the SUBBIMATT project to be able to share and to help you to introduce to the SUBBIMATT project and to give a bit more explanation of what we are doing. So, some general information which was already shared partly by Kate, I think important to know is that we started a good year ago in September 2024 and that we will be running for 4 years. We also have a website, so in case you want to have some more information on what is being taught today, you can always go there and have a look now or later on in the project. So, first of all, what's the overall goal of what we're doing in SUBBIMATT? We want to develop textile materials which are helping us to the needs of the energy management and the renewable generation of this energy. We want to do this by working on a stepwise trajectory, starting with the development of bio-based materials and textile intermediates. These are then being applied in our bio-inspired smart textile materials. And in the end, we will use these smart textile materials in our demonstrator use cases and actually applying what we have been doing in the project. All of this is being supported by the Safe and Sustainable by Design framework, and we will also be using modeling in order to further optimize our use cases. Next, I would like to show you the SUBBIMATT video, which was prepared by our project partner, which is nicely introducing the overall goal of the project.
Smart, multifunctional, sustainable. The world is changing fast, and so are the needs of the people living in it. We need materials that adapt to it, just like we do. Envision technical textiles that react to their surroundings, change, shape, and even harvest energy, all made from environmentally friendly, bio-based, and bio-inspired materials. SUBBIMATT is a 4-year Horizon Europe project aiming to bring this vision to life. SUBBIMATT will pioneer a new generation of smart materials by developing a wide array of innovative solutions, including advanced coatings, nanomembranes, and shape memory textiles designed to respond to a variety of external stimuli, such as temperature, pressure, motion, powering the next wave of circular and intelligent textile systems. These new smart materials will be showcased in 3 demonstrators: adaptive building envelopes that track solar radiation for on-demand shading or energy harvesting, automotive interiors capable of generating their own energy, technical garments with tunable breathability. Inspired by nature, these textiles will open, close, bend, inflate, and generate clean energy, just like plants responding to their environment. A safe and sustainable by design approach will guide every step from raw materials to end of life, ensuring performance, circularity, and safety. SUBBIMATT will help shape the next generation of smart, sustainable technical textiles, supporting Europe's transition to a circular and climate-neutral future.
Okay, so far the video of the project. Let's then have a bit of a closer look to the different steps and the different research that we are doing in the project. So as mentioned earlier, we start with the development of our bio-based and bio-inspired materials. Some examples of developments which are being done in the project are debondable adhesives, with the goal to, for example, remove the coating from the substrate once we are going to the recycling phase. Further, we are also working in bio-polyurethanes, which have a self-healing functionality, which will be the topic of today's webinar, and then also bio-based polyurethanes with shape memory features. In addition, we are also working on negative thermoresponsive materials, which will be reacting differently to temperature. So these bio-inspired materials are then evaluated on the one hand regarding their performance. This is not only the standard performance, like for example strength, which is of course of importance if we want to apply our textiles, but also the functionality that we are adding, like for example the self-healing. In addition, we are also looking to the circularity, taking into account that the materials have to be easily recyclable or biodegradable for certain applications. So once we have made a selection of the most promising materials, these will be processed using standard textile processing technologies into our circular textile intermediates. Examples of these are the coated fabrics, the functionalized nanomembranes, and functionalized filaments and fabrics. These textile intermediates are then next applied into our smart textile materials. The ones we are developing in the project are as first the inflatable textile actuators, which is a soft pneumatic actuator using an inflatable system of coated textiles. The second one are the textile energy harvesters, using the piezo and triboelectric effects to generate energy. And the last one are the tunable openness fabrics, changing a fabric which is changing its openness depending on temperature, both in a passive as well as active way. Once we have our smart textile materials, we go into the next step, which is then actually applying our developments into use cases. Use cases within the project are the building envelopes, a garment with tunable breathability, and the automotive interior parts. This selection was based on the one hand, we made the choice to work with actuators and harvesters because textile-based sensors, communication units are already more advanced. So we started with things which need some further research work still to be done. Also, the selection of use cases covers quite some technical challenges which are still out there. For example, the fact that they have to be durable in outdoor use, the fact that it's kind of a complex structure, and then as another example, we have the washability if you're working with garments. And of course, all of them are contributing to the needs that we have for the energy management. In the next slide, I'll shortly introduce each of the three demonstrator use cases, not with the goal to give you a full overview. For that, I kindly guide you to our website and to the partners who are working on these use cases. So the first use case is the building envelope. Here we are using a flexible membrane with two airtight chambers, in which a differential pressure in the two chambers will enable the activation mechanism to start. In this way, we will be able to track sun radiation and also to harvest energy using the vibrations which will be anyhow present into the use of the membrane. In the end, we want to get higher energy savings when we would compare it to static alternatives, which are, for example, also giving shades to sunlight. The second example or the use case are the automotive interior. Here we will be integrating piezo and triboelectric energy harvesters in the automotive parts. The goal is that actually the core parts will be able to generate energy and to self-power as much as possible their integrated sensors and actuators. In this way, we can avoid the use of wiring. We will be applying these textile energy harvesters both in the seat with the goal to harvest vibrations as well as friction, and then also in the door panel or in the headliner with the goal to harvest the vibrations of the car. And then we have our last use case, which is the outdoor fabric. So here we will have a fabric which has a tunable openness. We will also integrate some energy harvesting inside its material in order to, for example, to give some energy to sensors. And then we will integrate the openness fabric using our shape memory bio-polyurethane filaments and the negative thermoresponsive materials as a finish. So this, in a nutshell, are demonstrated use cases. As said, more information will come later on in the next webinars or on the website of the project. What I also would like to mention, you have seen that we are developing SUBBIMATT in different steps. So we start with the development of our materials, we go to the textile intermediates, and then in the end to the smart textile materials and the demonstrators. The goal is that actually in each of these steps will lead to results that are exploitable and that can be applied in other applications as well. So each of these steps will also generate some public guidelines, which will be available to you to have a closer look and to see what could be done with our developments in your work. I would also like to mention that liaison is an important part of the work in SUBBIMATT, so we will also link with what's ongoing behind or beyond SUBBIMATT and to integrate it into our developments. So if you have anything linked to our developments, feel also free to reach out. You have seen SUBBIMATT is a quite ambitious project, so for that you also need an ambitious consortium, and luckily we do have it within our project, so we have a nice group of partners working together to reach our goals. This is including our end users in each of the 3 applications. We have our companies which are focusing on the R&D, for example, for the developments of the coatings, and then we have the RTOs and universities supporting the research work. So far for the introduction to SUBBIMATT, and I will now give you the word to my colleagues who are working on the self-healing part to give you some more detailed information on this research. Thank you very much for your attention.
Thank you also, Lynn, for this very nice overview of SUBBIMATT project. This was an initial introduction, and also would like to thank Andrea and Tinexta Group for the very descriptive video. It was a very clever way that we have shown our scope and objectives. So it was a very nice introduction, and I would like now to go to our second session, where insights for the design of sustainable and healable polyurethane materials will be presented by Dr. David De Smet and Dr. Pegas Zahedifar. I would like also to give a short introduction about David and Pegas. So David obtained his master's degree in chemistry from Ghent University, from it also obtained his PhD in pharmaceutical sciences a few years later. And since 2011, he's working at CENTEXBEL as a research scientist in the group of coating and finishing technologies. His field of expertise includes the implementation of biomaterials and eco-friendly materials in textile coating and finishing. And also, David is a distinguished speaker for us today because in 2015 he received the Textile Innovation Award in the category of new materials. On the other hand, Pegas holds an MSc in Material Science and Engineering from Sharif University. And she has also industrial experience in active pharmaceutical ingredients. Her doctoral research was in biomedical engineering at the Ghent University, and she has focused on plasma polymerization techniques and tissue engineering. Pegas joined CENTEXBEL as a researcher, where she currently works on the development and application of bio-based materials for textile coatings and smart textiles. And her research bridges sustainability and innovation, aiming to enhance the functionality and environmental impact of textile products. So in this second session, we will focus on the evolution of polyurethanes, beginning with fundamental chemistry principles and their environmental impact, and progressing towards bio-based polyurethane solutions that align with circular economy principles. So I would like to give the floor to both speakers to start with their presentation. Any question that you have can be written down in the chat, also for Lynn. And at the end of this session, that will last for half an hour, we will have all the descriptions related to the sustainable and healable polyurethanes. So please, you're free to start. I think Pegas will be at the beginning, and then David will continue. So Pegas, the floor is yours. Thank you.
Thank you, Kate, for the nice introduction, and hello everyone, good afternoon. I will explain a little bit first about the polyurethane and how to design it in a more sustainable way, and then we will dive into the self-healing properties of the polyurethane. So we are actually surrounded every day with polyurethane, from the foam that we have, that we sleep on it, until the clothings that we have or the paintings on the wall. So this polymer is everywhere in our daily life. And to see what exactly is polyurethane, so if we have a polyol that is made of a chain of polymer that contains a lot of hydroxyl groups or the OH groups, and if we react it with the isocyanate, which has this N double bond C double bond O functionality, and then we will have the urethane bond with this kind of structure. And only if we can talk about the European region, every year 3 million tons of this polymer is being produced, and it can be used in different kind of applications, from foams to coatings, elastomers, adhesives, and biomedical field. So it is a big share in the production of the polymers. And now how we can exactly change the properties of polyurethane. Polyurethane is consisted of different parts, such as the polyol. So if we can change the type of the polyol, then we can change the properties of the polyurethane as well. And the other part that is also important is the type of the chain extenders or the capping agents that we are using for the production of the polyurethane. And this is also effective on the final properties. And the other part or the other building block that is also important is the type of the isocyanates that we are using for production of the polyurethane. And these are the most effective building blocks on the final properties of the polyurethane. As I mentioned, one of the most important building blocks are the polyols that we are using, and we can change the properties, or we can categorize actually the polyurethane type based on the polyols that we are using. So we can have, for example, polyether polyols, polyester polyols, polycarbonate polyols, or the blending of these polyols together. And each of them have different properties, like for the polyether polyol, for example, we have poor weather stability, but the hydrolysis resistance is a good one. For the polyester, it is vice versa. And for the polycarbonate, we have both good weather stability and the hydrolysis resistant. And with combining all of them, then we can have the optimized polyurethane based on the final application that we have in mind. Another conventionally, the polyurethanes used to be made in the organic solvents, but nowadays we have a more greener version, which is the water-based dispersed polyurethane that we call them PUD. And for them, we have several steps for the synthesis of this kind of polyurethane, which is first we synthesize the prepolymer. That is the reaction of the polyol with the isocyanates and addition of the catalyst. And we also need to add the internal emulsifier in order to be able to later disperse the polyurethane in the water. And then in the later stages, we will add the chain extenders or the capping agents to the structure of the polymer. And then at the end, we need to neutralize the internal emulsifier that we added in order to disperse it in the water. If we look at the life cycle of the polyurethane, we can see that we have different stages of the production and the use, and at the end they are mainly incinerated or landfilled. And if we look at all these stages, we can see that for all of them we are using a lot of energy, and also we are emitting a lot of gases to the environment, and all of them are affecting the environment as well as the human health. And so in order to optimize this and have a better effect on the environment, so we should have another approach, which is the sustainable polyurethane. If we look at, for example, the CO2 emission for the polyurethanes that are in the market, and for example, if we look at the initial bars in this figure, if the polyol that is used in the production of the polyurethane, it is based on the crude oil, we can see that the emission of the CO2 is a lot higher than if we go to the end of the figure for the more greener alternative, which is, for example, the waste cooking oil. So if we can replace the building blocks of the polyurethane with a more greener or bio-based ones, then we can affect the CO2 emission and the environmental impact in a great way. And one of the alternatives to the crude oil or crude-based polyols are using the bio-based and especially the second generation bio-based alternatives. And for example, the second generation alternatives are coming from the waste of the food industry or inedible oilseed crops, or the ones coming from the wood biomass, and also the post-industrial recycled polyols. And in this way, we can have effects on the sustainability of the polyurethanes that we are producing. On the other hand, we can have alternative to the other building blocks. For example, we can replace the catalysts that we are using with a more safer or less toxic ones, or we can replace the aromatic isocyanate with aliphatic ones, which are less toxic, or we can replace the building blocks with the more bio-based building blocks like the polyol, as I mentioned. Or we can change the media that we are synthesizing the polyurethane in it with the, for example, the water-based media that was mentioned earlier. Or we can extend the lifetime of the polyurethane. For example, we can have the self-healing polyurethanes that can extend the lifetime of the polyurethane, and then in this way we can also have it more sustainable. The other approach is that we can affect the end of life of the polyurethane. For example, we can have biodegradable polyurethane by incorporation of the biodegradable linkages or building blocks in the polyurethane. Or we can have recyclable polyurethanes, or that's, for example, we can incorporate chemical degradable units in the polyurethane backbone, or we can chemically or enzymatically recycle the polyurethanes that are produced, or we can reprocess the polyurethane. So for example, if we can have the thermoplastic polyurethane instead of the thermoset one, then we can reprocess it and reuse it. But when we are going for the bio-based alternatives for the production of the polyurethane, we are achieving some good aspects, but we are also losing some of the properties. For example, if we can have the petroleum-based one, the performance of the final polyurethane is much higher with regards to the mechanical properties or stability, and the scaling up, the process for the scaling up is already optimized in the industry, and we can have better scale up productions, and it is more known to the market, so people are more willing to buy it at the moment, and the efficiency is also proven. But on the other hand, if we go for the bio-based alternatives, we will reduce the carbon footprints and we will have more renewable and waste-derived sources for the building blocks, and it is gonna be more safe and non-toxic, and it will be biodegradable. And also, due to the legislation, the market demand is also increasing. If we look at the application of polyurethane in textile, we can see that we have polyurethane in many applications, such as the technical textiles and protective clothing. So it's a really large application for the polyurethane in the textile field. And if we look at how we can apply the polyurethane on textile, we can have different methods. For example, we can have or we can apply a coating on top of the textile, which we can use the knife over air coating, which is the first demonstration here. And in this one, we can apply the coating while we are dragging the textile, and the knife is a stand or still. And the other alternative is that we can drag the knife on top of the textile and apply the coating on top of the textile, which is more prevalent method for applying the coating on the textile. The other alternative is padding, which we apply a treatment on the textile in the fiber scale, and this is the way that we have to dip or immerse the textile in a bath that contain the polyurethane, and then we drag the textile and squeeze it between two rollers in order to get rid of the excess amount of the polyurethane, and then we have the drying and curing steps. Each of these methods have their own properties and advantages and disadvantages. For example, if we apply a polyurethane based on the coating application, then we will have a significant amount of the formulation on top of the textile, and it will have a much higher durability and barrier properties for the textile. But on the other hand, it will be a visible coating on the textile, and it will have some negative influence on the flexibility and breathability of the textile. And some of the examples of this kind of applications is, for example, for the waterproof textile or architectural textile. On the other hand, if we apply the polyurethane in form of the padding, then we will have only the treatment in the fiber scale instead of the whole area of the textile. Then it will be less visible and less effect on the properties of the textile, and it will still be breathable, but the stability of such kind of treatment is much lower than the coating. And some of the examples are like water repellent textile or softened textiles. Now, if we go for the SUBBIMATT, as Lynn mentioned, we have this demonstrator that is the building envelope, and because they are prone to mechanical forces, then they will have some damages on them. And if we can have a self-healing layer on top of these envelopes, then they can restore their properties after a while, and then the um, end of life of them would be a lot more sustainable. And now about the self-healing properties. Self-healing materials are the one that can automatically repair their damages without external intervention. And so they can restore their properties or functionalities without an external intervention. And this kind of properties can be intrinsic or extrinsic for the material. The intrinsic one are the one that they have some reversible linkages inside of the chain or inside of the structure of the material, and upon a external or a trigger, they can actually rebond this linkages that they have, and they can restore their properties. The extrinsic ones are the ones that some kind of microcapsules are incorporated to the structure of the material, and upon the crack or the damage, these microcapsules will release some material that then they can heal their properties after a while. To have a more a demonstration of how they are going to work, if we have a substrate and on top of it we have the self-healing polymer, then upon the defect we will have a crack or a damage, and if we apply, for example, the external stimuli like the heat or for example UV light, then the intrinsic self-healing polymer will start the healing process, and then the crack will be reduced and until it is completely healed, and we will have the original properties of the polymer on top of the substrate. And these kind of polymers can be used in many applications. For example, they can be used in biomedical applications, e-skins and electronics, and construction, energy, coating and surface protection, as well as the transportation. And the self-healing coatings can have a lot of benefits. For example, they can extend the lifespan of the material, and then we will have less need for replacement or repair of the material. They can maintain their performance for a longer time, and they can reduce the maintenance cost, because then we will need less repair and replacement, and it will be much more sustainable. And then from here, let me see, so I cannot give the control. I will unshare. Okay, so I will give the floor to my colleague David, and he will talk more about the polyurethane, self-healing polyurethane.
Thank you, Pega. David, are you ready? We cannot hear you yet.
Yes,
Perfect.
but I'm looking into
Mhm.
my PC is a bit slow. Yes, so thank you, Pia, for the nice introduction about proteins and self-healing. So now I'm just going to combine both. If you just can remember, Pia said that way to get polymer healable is by using intrinsic and extrinsic healing. So if we are focusing that on protein, that means in case of intrinsic healing, we can use containers or microcapsules embedding isonates into a coating. So that's way when there's a crack is happening, the microcapsule will be destroyed, and then the isonate can flow into the coating and react with some remaining OH groups to get again a polyurethane. This actually is not really limited to one type of isonates. You can use aliphatic and aromatic ones in that type. Of course, as Pega mentioned, this is only single ones restoring or repairing. So that's why we are looking into intrinsic healing, in which we use reversible bonds within the polyurethane. And if if we are looking to that, we can make a distinction between reversible covalent bonds and reversible non-covalent bonds. So ways of covalent bonding are disulfides, for instance, these other bonds, imine bonds, etc. Those are reversible covalent bonds, which can be broken and reformed again. Another way of intrinsic healing is looking at the non-covalent bonding, and this, for instance, are like ionic interactions, hydrogen bonds, pp stacking, etc. Of course, those bonds are normally less strong compared to the covalent bonds. If we just look at the different options we are looking at in the SUBBIMATT project, then we are focusing on the intrinsic healing and mainly on the covalent healing, I would say, so the covalent bonding, and therefore we are looking into these other reactions. It's just an easy way to reshape also the polyurethane coating as well, so you can easily break and reform the product. Same with using disulfide bonds. So disulfide bonds are also known for hair. So you can go to the hairdresser and make some curls in your hair. This is based on the disulfide, and over where and you can see by temperature you can change the curling behavior of the hair. That's because the disulfide bonds will be broken and reformed. Then we have also SIF-based, so imine bonds, which are also known to be reversible, as well as boronate ester bonds. So those are the type of bonds we are looking at into the SUBBIMATT project. Of course, once you have a healable polymer or polyurethane in our case, you want to know how to test it. So therefore, you can have different test methods to assess the healing. So first of all is when you make a crack or you break a coating into two, can we recover it visually? Can we still see a scratch? Do we can get do we can glue actually two pieces into one piece again? I would say so. Join it back, and afterwards, of course, the question that still remains is the coating still strong enough as originally? So therefore, you also need to do some tensile strength measurements as well. And then also what can be looked at is the restoring of the water barrier properties. So in our case, at the moment, we are looking at the tensile strength. So actually, this is measuring the strength of the coating before making a scratch, and then after making a scratch and healing it. So then by just comparing the tensile strength before and after the healing process, you can have an idea about healing efficiency. So by just doing the ratio of the two and multiply by 100%, you have a healing recovery percentage. And this is shown here in the table for different formulation. And it's clear here that for most of the formulations we made, we have a good healing behavior, which in most of the time is above 80% and also are around 100%. So here we can already see that not only visually we can see a restoring of the coating, or we can join two broken parts into one, but also the strength is recovered. Of course, also the water barrier properties are important, and therefore we also are assessing and comparing the water properties of an original coating, of a damaged coating, and then of the damaged coating after healing. So this is also done here for the SUBBIMATT sample. So originally we had a polyester coated with the self-healable PU. Originally the water barrier was minimum 1000 millibars, so this is the maximum value which we can measure. Then we put a scratch under the coating, and then we see that the water barrier properties is dropping from 1000 down to 118. Once we do the healing test, we can see that we can recover the water barrier properties, since we have again resistance to hydrostatic pressure of 1000 millibar. Another way, as already mentioned, to assess the healing behavior is just by looking at it with the naked eye. So, like for instance, with optical microscopy. And here you can see it clearly from the coating. This one of the examples of the formulation that we have is that at the left you can see that the scratch we made, and then after just heating, in this case it was at 80 degrees, you can see that the scratch is gone for both scratches. So we made a scratch with 2 Newton and 5 Newton, and in both cases the scratch is gone. What we also can do is you can look into a more detail into the scratch by using scanning electron microscopy. And here you can also see at the left, you can see the damage made by the scratch into the coating. But just heating it at 80 degrees, you can see that the coating again will restore itself. Another way is just to break a film or a part of a coating into two, and just again afterwards you can just place those two parts close to each other. You heat it in the oven, and afterwards you look if the two parts are joined or fused together. And here you can see that of course the two parts are joined again into one piece. This can be done by just a normal melting process, of course. So that's why it's important also to do afterwards a tensile strength test. And as you already saw from the previous slides, we can recover our tensile strength. So it means that there's no melting behavior, but there is really a chemical healing process taking place. Of course, the goal of the SUBBIMATT project is to get a sustainable polyurethane, and as mentioned by Pega, it's not only about self-repairing or self-healing, but it's also looking at the end of life. So therefore, we also are looking to different options how to deal with the end of life of self-healing PU coatings. Therefore, we have different options present. So there is a debond on demand coating, which enables us to separate the coating from the textile, so which enables us to afterwards recycle the textile. Or it's also possible to do isovolysis of the coated fabric. The idea of this process is to chemically recycle the PU coating, and to also to separate the coating from the textile in one step. So it's a chemical recycling process, and this is possible via glycolysis, hydrolysis, aminolysis, and transurethanization. But you can also do alcoholysis, so which is a derivative of hydrolysis, in which you're using alcohol instead of water. And then the third way end of life we are looking at in CENTEXBEL is a biodegradation of the PU coating. So first of all, I'm just going to introduce like a debondable bio-based polyurethane. So there we are looking into incorporating degradable units into the PU backbone, so chemical degradable units, and therefore we are looking at silyl ether groups which can be incorporated into the backbone. Silyl ether groups are also used in organic chemistry as a protective group, and it's known that in case of presence of fluoride ions, these will be easily cleaved, and so the idea is if we can incorporate this in the PU backbone, maybe also your PU backbone will be cleaved. So this is just a schematic overview of how it looks like. So you have your coated polyester textile with a pure coating. You need to shred it in piece, and then we put it in a 2% solution of terbutyl ammonium fluoride. And if you let it stir at room temperature for 2 hours, you will see that the coating will be removed from your textile. And by just a simple filtrating process, you can separate your recovered polyester textile and your degraded polyurethane, which is still in the solution. Just some pictures how it looks in real life. So at the picture above shows you a cross-linked PU coating, which was dissolved in 2% of terbutyl ammonium fluoride in a solvent at room temperature. The solvent is necessary, of course, and will depend on the hydrophobicity of your polyurethane. In our case, it's a bio-based polyurethane, which is hydrophobic, so therefore we need a hydrophobic solvent. In case you are having a hydrophilic solvent, then it's possible to use water or an alcohol, because the solvent has to give accessibility to your fluoride ions to the PU backbone. So therefore, it's important there's some, I would say, compatibility with the solvent of the solvent with the polyurethane. So if you just look to the picture, then you can see that the cross-linked PU coating is completely gone. So it's completely dissolved into the solution. While at the pictures below, we actually did the same experiments, but with just a reference PU. So meaning that we didn't use any silyl ether diol in the backbone. We used still the same compound, the same isonate, the same polyol. And it's clearly seen here that the PU does not degrade. So you can see that your solution is not transparent, and after filtration you can still see a clump which is remaining, which is still your polyurethane. If you just look to the analysis of your fabric afterwards, so which you can recover after the normal filtration, simple filtration process, then you can see from infrared analysis that there's actually no really significant chemical difference or chemical peaks difference in the version and the recovered pad. So meaning there's no chemical degradation of your polyester. Also, if we look to the SAM, so scanning electron microscopy, we don't see any degradation residue or impurities from the process on your polyester fabric. If we also look into other properties of the recovered pad, then we see that the thermal degradation of the recovered and the original pad is almost identical. We only saw some small changes in thermal properties like glass transition, melting, and crystallinity degree. We saw that in case of the recycled pad, there was a low decrease in the TG, so the glass transition temperature, the melting point, and crystallinity. Another way, as mentioned, is also for end-of-life option is to look at solvolysis, so chemical recycling. So in this case, we give an example of solvolysis of a 2K PU-coated fabric. So we did it in case of an acid-catalyzed depolarization in presence of water. Afterwards, the PU was degraded, and you can simply recover the fabric by a filtration process. On the fabric, again, we did the same test as was discussed previously, and again here we didn't see any degradation issues or loss of mechanical properties as well. So just at the right, you can see the infrared analysis. Again, you can see that the peaks are quite the same, so there's no chemical degradation or hydrolysis of your polyester during the recycling process. Of course, in case of chemical recycling, it's also important to retrieve your polyol and your isonate compound. So therefore, we also had a further purification of the different degradation products. And actually, we could retrieve both the polyol as well as the amine, which is derived from our isonate. At the left, you can see the infrared spectra of your polyol, of your original polyol, which in this case we used was 3172, and then of the I would say the retrieved polyol, so your degradation product. We can see that the peaks are almost the same except for one peak. I also indicate that on the slide, which we saw there was an aldehyde peak. So during the chemical recycling process, the polyol is formed, but a part of the polyol is oxidized into an aldehyde. So this is something that we need to look further in by, for instance, changing the process conditions as well, because we try to reduce afterwards the aldehyde into the hydroxyl function again, but it was not possible to do it at 100%. So therefore we need to look back at the process conditions and, for instance, work in nitrogen, so inert atmosphere. If we just look at the right, then you can see that next to the polyol, of course, you also have your isonate compound. Because of the hydrolysis, you cannot retrieve your isonate compound as such, but you will retrieve your amine. In this case, for the 2K polyurethane coated fabric, we used a Desmodor Eco 7300, so bio-based isonate from Convestro as isonate source. And if we compare this with the product we found, then we can see on the infrared analysis that some peaks are corresponding, while others are not. So for instance, like in the blue line, we can see that we have a peak of 2250, which is the isonate peak. Of course, this is gone. But on the other hand, we can see that there's a peak arising above 3000, and this is typically for amines. In this case, we also see peaks at 1550, which is typically for primary amines. So taking all those peaks, I would say, into account, we can conclude that we retrieved the primary amine of the isonate which we used to make our PU coating. So we were able to retrieve our amine in high purity. We also were able to retrieve the polyol which were originally used, but we had some impurities because we had some oxidation of the polyol into aldehyde. Next to that, we're also looking into solvolysis of PUD coated fabric, which is, I would say, a little bit more difficult, because in case of PUD coated fabrics, we will also use cross-linkers to have a better durability, which is not used in case of 2K, because 2K already on their own have a good durability. Why PUD is less durable? That's because we need to add some ionic groups into your backbone to make it dispersible in water. So during the process, during coating, we need to add additives to really block these ionic groups to get a better durability. And of course, by adding these additives, you will complex the chemical recycling process, because there will also be other compounds next to your PU into the coating. We already did some trials, and we can see that we can, I would say, degrade the PU coating. We can also recover purely the polyester fabric, but if we just focus on the PU coating, then we can still see with infrared analysis that the degradation of the polyurethane is not completely. So we can still see some urethane peaks, which were here indicated by the arrows. So above 3000, you can see a small urethane peak, but also a shoulder around 1700, which is the carbonyl urethane you can see. And also you can see a little bit of the CN amide stretching just above 1500. Again, it's really a shoulder, so it are not high percentages, but it's not completely. There's still, I would say, estimation of about 10 to 20% urethane peaks present. So we need to further optimize the chemical recycling process. Another way that we also have looked at, and it's also a possibility which is going to be explored in the SUBBIMATT project, is to use a biodegradable polyurethane. Unfortunately, the biodegradable polyurethane in our case now is still not completely bio-based, because the polyol is not bio-based. Again, here I just will focus on the results of the biodegradation process. So here we did an ISO test at 25 degrees, so a sole condition test of a cross-linked PU coating. We put it in the sole, and after 3 months we had a look to the biodegradation of this PU coating. And we could see that after 3 months, the coating was 50% biodegraded, which is quite a lot, because normally PU coatings are not biodegradable. And we could also see that we don't see any effect when increasing the crosslinker. So this is very promising. To have an idea, after 3 months, the cellulose, which is your reference material, had a biodegradation of 70%. So we are already at 50% or are close to it. So relative to the cellulose, we have a biodegradation of 70%. Maybe as well to mention, the coating itself has a very high hydrolysis resistance, but also a high washability. So because it's cross-linked and it's biodegradable, so really to get the combination of the three is very difficult to get. But at the moment we are succeeded in that. Of course, it's not all about biodegradation, because during the biodegradation process, you will have degradation of your compounds into new compounds, like CO2, for instance, but also other compounds. So therefore, it's important that those compounds are not toxic. So therefore, we also did do a plant toxicity test. So what we did is we seeded cress seeds and lettuce seeds into soil, which was a control soil, but also a soil with the pure coating. And afterwards, we looked at the germination rate and the fresh weight yield of the cress and the lettuce after some time. And if we just look to the values at the left in the tables for cress and lettuce, we didn't see any significant change between the germination and the fresh weight yield of cress and lettuce in a normal soil or also a ground with a pure coating into it. So therefore, we conclude that we didn't see any toxic effects at this moment with those testing. Next to that, of course, if we just look to biodegradable packaging, they all will also do a metal analysis test. We also did it with our pure coating, and we could see that we almost saw no presence of metals except for a little bit of zinc and fluor, which were present in our original molecules like a polyol, catalyst, and isonate, but we were far below the limits set by the ENS standard. So this was a little bit our presentation from me and Pekka concerning polyurethane, but also to make it self-healable and to make it more sustainable by also looking at the end-of-life options. So if you
Thank
have
you
any
very much.
questions, please feel free to ask.
Thank you, both of you. And it was really nice to see the developments within CENTEXBEL for SUBBIMATT project and to meet the team. There are already two questions placed in the question and answer session. I will start by reading the last one, which was related to the final part that you presented, David. It is from Oscar Calvo, and it's mentioned about the debonding routes for coatings. So, what is your opinion about the enzymatic assisted processes for removing coatings and finishings, even dyes, from the fabrics? And is there any previous experience on this?
Um, Yes, we will start a project in February next year, looking into enzymatic recycling of bio coatings. So for sure, we will look into that next to chemical recycling, as it's a more green process, more environmentally friendly. Also, most of the time, lower temperature, atmospheric pressure. So it looks fine, but the problem is, will it be efficient enough? That's something that we had to look at. There are some options in the literature which are describing the use of urethanase, hydrolysis, as well as esterase. But of course, esterase can only be used for polyester polyurethane. So this already has its limits. Concerning our experience, we only have experience with some of the polyurethanes, which we did in a preliminary test. We tested our biodegradable polyurethane as well as some two actually commercial polyurethanes. We didn't see any enzymatic degradation of the commercial polyurethanes, but in case of our biodegradable polyurethane, we saw a degradation. So probably the enzymatic recycling will be depending on your type of PU. So actually in our project, which will be starting in February, we will actually design the PU in ways that it will be, or we hope that it will be recyclable by enzymes. So by incorporating esterase bonds, but also bonds which are a little bit more sensitive to hydrolysis, for instance.
Very nice. I guess that this has answered Oscar's question. The second one, and you're free to decide who would like to answer this. It is from Guillermo Ormazabal. there is actually doubt if the polyurethane coating is applied to the filament before the fabric is produced or directly to the final fabric.
So in our case, is the one that I explained. We apply it directly on the fabric, so the final textile. But in some of the special cases for some industry, they also use yarn coating. But in our case, it is applied on the textile or the fabric itself.
Thank you, Pega. Since I don't see other questions right now in the chat, I would like to make a question to you both. And for me, it's important to explain how you identified which bio-based raw materials are the optimum for these developments, because there is a wide variety of possible alternatives. So, what is
Mhm.
your decision mechanism?
Yeah. So actually, we have already some experience in the past concerning the selection of building blocks. So first of all, I will also say with the isonate, we are looking into aliphatic ones because aromatic ones could be more toxic. Also, at the moment, the end of life still of PU coatings is still landfill or incineration. And during that process, aromatic amines can occur or arise, and those are more toxic compared to aliphatic amines. So that's why we choose in case of aliphatic isonate. How we choose the bio-based polyols. First of all, we know we are choosing on the molecular rate. So we are focusing on the molecular rate between 1000 and 3000. And then we're also focusing on hydroxy value. In case of textiles, it's important that the textile is still, of the coating is still flexible and elastic. And therefore, we need to tune the hydroxyl value in order not to have a very high cross-link density of your polyurethane at the end. So in meaning that we need to look at polyols with a quite lower to moderate hydroxyl value instead of a high hydroxyl value. So this is our first way to select the polyols. And more into the SUBBIMATT project, of course, we mentioned that we would look to bio-based materials and moreover to second generation biomass materials. So based on those criteria, we made a selection of a couple of polyols.
Good and very interesting. Thank you, David, for your answer. Okay, so there are no questions in the chat box. Can I see any raised hands? Someone would like to ask something more for mainly the technical insights that have been shared? Not yet. So last question from my side regarding the technical part. How are you able to balance the mechanical performance together with the flexibility and the sustainability? Because I think that Pegaf showed a trade-off between the properties, and this is quite important, especially for the applications that are quite diverse in this project.
Yes, it's always, I would say, sometimes it's testing and see how to improve it because you cannot really predict everything beforehand. Of course, we have some experience. Like also Pea showed that depending on the type of polyol, you can know if will it be, for instance, sensitive to hydrolysis, will it be sensitive for weathering or not. Then, of course, we also need to attend or make some attention to the price of the product because polycarbonate polyols are the best ones, but are also more expensive and they are not really bio-based. If we just look to bio-based, then we are already looking into the polyester polyols. And then concerning mechanical performance, we are looking already to amorphous systems as well, so not crystalline systems in our building blocks to have a good elongation, for instance. And then to get, if we can see, for instance, that some properties are not okay, then we need to add some additives. This is also a trade-off. For instance, we need to add some crosslinkers to make it more durable over time, the coating. But of course, when you make some crosslinkers, you will have a thermoset system, and therefore the self-healing performance could be decreased. So it's really a trade-off into selection of the type of additives in that case, but also the level of additives, because they can have an effect. As well as, for instance, some of the healing processes based on radicals. If you would add UV absorber, for instance, to improve UV resistance, this can also have an effect on your self-healing process, because the radicals will be scavenged by the UV absorber. So this is really a trade-off, which we have some experience with it. Some things you can already predict, but some you need to test and see if it works or not.
Thank you, David. It was very informative. And also your session detailed in terms of experimental. We have been deepened in the chemistry of polyurethanes, and this is actually the scope of these webinars, to have an informative and training aspect for all of us working in this field. Lynn, do you have any closing remark? Because now the time is running out.
Yes, I think time is running out, so I would just encourage everyone who has any further questions, comments, or feedback to reach out to us. We are very open to further discuss.
Thank you all. Please stay tuned, because there will be also extra webinars that will be held during next year. We will have 2 webinars each year, and we'll be sharing the developments of different partners within SUBBIMATT, always with an educational and training scope. So the next webinar will be organized within the spring of 2026, and probably be related to the openness fabric operation with hydrogels that have been produced by NTUA. There are some information in the chat from shared by Andrea, where you can follow the SUBBIMATT website and also follow the webinars. So I think that that's all for today. Thanks again to our speakers and to CENTEXBEL team, both for the coordination of SUBBIMATT project and their technical developments. And have a nice afternoon. Thank you all.
Thank you for moderating, Kate.
Thank you.
Thank you. Have a nice
Bye.
day. Bye bye.
Bye-bye.
Goodbye. Stay tuned.